Welcome, everyone. Thank you so much for taking the time to be here listening this EC Distinguished Senior Speaker talk today. So today it's really a pleasure to have Justus Ndukaife as our guest speaker. So Justus received the Bachelor of Science degree in Electrical Engineering from the University of Lagos in Nigeria. And after that, he moved to the US, where he got his Master and PhD in Electrical Engineering from Purdue University, working on Plasmonic optical tweezers. So in fact, in recognition of his contribution in this specific field, now Professor Ndukaife received the prestigious Physics Prize Award by the Dimitris Kollafas Foundation in 2017. And as I understood it, this is a very prestigious award since it's given to the best doctoral candidate at Purdue every year. And starting in 2017, he has been assistant professor of electrical engineering at Vanderbilt University. And so during his career, he has already received many prizes. So I'm going to mention a few of them. The Purdue College of Engineering Outstanding Research Award, the NSBE Golden Torch Award, Best Paper Award at the ASME Conference, the Carnegie African Diaspora Fellowship, and lastly, the Vanderbilt Provost Research Studios Award. So it's really great to have him here. And so today he's going to talk about Optical-Thermo-Electrohydrodynamic Tweezers, a new paradigm in optical nanomanipulation. So with that, so again, thank you, Justus, for taking the time for giving this webinar, and feel free to start whenever you're okay.
Okay, great. Yeah, thank you so much, Alessandro, for the terrific introduction, and thank you all for participating. It's really a pleasure to get to give this seminar virtually, and also to get to discuss about the latest advances in the field of optical nanotweezers, as well as our latest works in the field. So as I begin the presentation, I'd like to show you a quick video, which will basically summarize what I'm going to be talking about here today. So this portion here, an array of plasmonic nanoholes, which will illuminate with a laser beam. And then we show that we can trap sub-10 nanometer sized objects, such as small protein particles, at distances that are far away from the laser beam. So we can actually make these particles to feel a distance, feel a force from a distance. And this makes it possible for us to mitigate any issue of potential, or any potential issue of optical damage to the biological molecules. Trapping such small objects with optical tweezers, is extremely challenging. You're basically going to opticoat the materials, but here we show that we can do this for the first time. So in this talk, I'll be discussing this concept and also why this is important and correlate to a lot of important breakthroughs in the bio and life science domain. So first of all, let's go back to the basics. So I'm sure that perhaps everyone here is familiar with the concept of optical tweezers. It's really a tool that can allow you to trap things on the micron scale, typically like bacteria and red blood cells. However, if you want to trap particles or objects that are very, very small, like below 100 nanometer, several of them include things like viruses, DNA, and protein molecules, which are extremely small. But you have to use nanotweezers to be able to do that. And there are several designs that have been implemented in the literature. And what I'm going to be talking about today is also a new way to do this kind of nanotweezing. But let's talk about optical tweezers. So I'm sure everybody knows that back in 2018, almost 2 years ago, Arthur Ashke was greeted with the wonderful news that he's been recognized with the Nobel Prize, one half of the Nobel Prize in physics for the development of optical tweezers. So he began the oldest person to win a Nobel Prize. And this was for his seminal contribution that he did back in 1986. So it was a very, very interesting thing to see, especially for those of us that are working in the field, because this tool has really had an enormous impact in the field. So really, what are optical tweezers? So the experiment which Ashke did back in 1986, or which he published in 1986, is the idea is as follows. He basically takes a laser beam and he tightly focuses the beam, and then when an object on the micron scale comes close to the focal position of the beam, the object gets trapped. So the key is to be able to focus the beam tightly. And when you do that, you're able to generate a strong gradient force. So that gradient force is proportional to the gradient in the square of your electric field, which is why you have to tightly focus the beam. And also the gradient force is proportional to the size of the particle to the third power. And this presents an important bottleneck, because basically what it means is, if you reduce the size of the object by just an order of magnitude, this force is going to reduce by 3 orders of magnitude. So that's an important problem. And also we know that in optics, we have the fundamental limit known as diffraction limit, which says that you cannot squeeze light below about half of the wavelength of light in a given medium. So we're always limited by diffraction limit. So for micron scale particles, you can really trap those. But if you want to deal with nanoscale particles, so we see the potential well is limited by diffraction limit. So they can really escape, due to the thermal energy, KT of the system. So this presents some challenges for using optical tweezers, to be able to trap things that are very small. So Ash can actually try to increase the laser power significantly. And if he does that, he noticed that he basically damages the particles, and that is a process he calls optication. So we have to find ways to overcome this diffraction limit so that one can use optical forces to be able to address very small objects. And that is really what gave birth to the field of plasmonic optical tweezers. So back sometime around, back in 2007, 2008 timeframe, researchers worldwide began to look into the concept of being able to use plasmonic structures which can efficiently couple to light to generate strong, a very tightly confined electromagnetic field, so that you can use that to be diffraction limit. And then that highly confined field can then exert forces on nanoscale objects to enable them to be trapped. So there are several designs that have been implemented in the literature, using, for example, gold nanodot array, or using a simple nanohole array, a simple nanohole on a gold film, or even by using a double nanohole configuration, which allows you to even generate a stronger confinement of the field, as well as a bow tie cavity, and also the coaxial antenna. So these several designs have really enabled us to address very small objects, using optical tweezers. And there are several other works from other groups, worldwide, which are listed here. I should also mention that beyond using the optical gradient force, people can also use another force that can be used by a laser beam, and this is basically the thermophoretic force, or the opto-thermal force. So you can use a laser beam to heat up a metallic structure, so it absorbs the light, generates some heating, and then the temperature gradient can induce a thermophoretic force. Usually this is repulsive, and by engineering your thermal landscape, you can make particles to be, for example, confined, in the midpoint here by simply moving the beam around these hot regions where the metals are. Or alternatively, you can also induce an attractive thermophoretic force, which is a negative thermophoretic force, by charging your electrical double around your particle. So you can make the thermophoretic force to be attractive and be trapped right where the hotspot is. And this has been demonstrated by the Zen group at the UT Austin about 2 years ago. So in the field of plasmonic optical tweezers, there are actually two main issues that one has to be concerned about. So one of them has to do with the issue of heat dissipation. And the reason is because anytime you illuminate a plasmonic structure, you're always going to have the absorption of the light and the dissipation of heat. So this is always present. So there are several research activities focusing on using this heat dissipation, for example, for water treatment, or also for photothermal destruction of cancer, like the group of Naomi Hallas pioneered at Rice University. So that in those kind of applications, you can actually use those heat to great advantage. But in some cases, for the applications where you want to address biological molecules to trap them, so this heat dissipation can actually present some problems, because they can cause boiling, or also increase thermodynamics, like increased Brownian motion. So that needs to be addressed in that context and also be managed. And the other issue has to do with the issue of low speed and uncertainty. And this arises because of the fact that if you have your plasmonic structure and you illuminate with light, so you create your evanescent mode, or the optical hotspot, and this basically extends just a few tens of nanometers from the surface of your antenna, into the adjoining fluid medium. So that means that any particle that has to be trapped must diffuse, get transported from wherever it is in place, and then will get diffused close to this region where it can be trapped. And that process can take several tens of minutes to an hour. So it's because it's a random process. Random diffusion is very random. So those are issues that have to be addressed. So in order to solve this issue of random diffusion and plasmonic tweezers, so we previously introduced this concept of electro-thermo-plasmonic tweezers, where we harness the combination of plasmon-induced heating with an applied AC electric field to induce an electrohydrodynamic flow, which can rapidly capture small particles and transport them towards your antenna. So now, instead of having to wait for random diffusion, you just need to actuate the trap, and within a few seconds, you've transported a particle for trapping at a plasmonic hotspot. So you can now do this within a few seconds instead of having to wait for several tens of minutes. So this represents one way that we actually get to put the issue of plasmonic heating to use, just as people have also done for cancer treatment and so on. So this is one way to leverage this for optofluidic applications. And with respect to managing excessive heating effect, one can actually integrate a heat sink in the design. So this was a beautiful work done by the group of Kenkos several years ago, where they suggested placing layers of high thermal conductivity materials like gold and copper between your plasmonic antenna and the substrate. So in this manner, any heat that is absorbed by the structure gets dissipated into the substrate, and can reduce the temperature rise significantly. However, this was quite interesting and enabled a lot of interesting possibilities. However, the key problem becomes the fact that you have to still rely on random diffusion to transport your particles towards the hotspot before they can be trapped. And you also lose dynamic control of particles that are to be trapped. So these are important issues that have to be addressed. So what is going to be the desired tweezer that we would like to have? So it's basically to have the best of both worlds. One is to have the capability to stably trap nanoscale objects, including those that are in the sub-10 nanometer size regime. And that's a very particularly important regime for biological molecules, because many proteins and DNA are actually within this size regime. And this is usually very challenging to do with most of the tweezers that have been reported to date. And also you should have the ability to be able to rapidly transport your target nano objects to the trapping site. So you don't have to wait for diffusion to do the loading. And one should also have a mechanism to dynamically control the particles after trapping them. And also, once you have the ability to ensure that biological objects are not exposed to detrimental heating effect. So being able to achieve all this in one system is actually non-trivial. And to my knowledge, we haven't have a system that can do that. And that's what I'll be talking about, how we're able to solve that problem in a little bit. And another interesting possibility that I would like to have is the ability to be able to sort nanoscale objects. So usually most of previously reported tweezers are usually able to trap. Sorting is a different ballgame. So being able to have that would be very beneficial for a lot of applications. For example, there are some biological objects like extracellular vesicles that are released by cells. The cells used to communicate with distant cells. And these extracellular vesicles are usually heterogeneous in population. And there's still a long-standing challenge on understanding how size helps to detect the cargo context, like how much microRNAs or proteins are present, depending on the size, which is very, very important to understand cell signaling, and also they are used for therapeutics. So that's a big area of research. So having the capability to sort nanoscale objects, sure is going to help to address this kind of challenges. Okay, so for the rest of the talk, I'm going to introduce to you the concept of Opto-Thermo-Electrohydrodynamic Tweezers, OTET, which we recently introduced. And in doing that, I'll talk to you about the concept of a plasmon-induced electrothermo-plasmonic flow, and also the concept of AC electroosmotic flow, which we can induce by using an array, a discrete array of plasmonic nanoholes. And then I will show you how we can harness the interaction between this electrothermo-plasmonic flow and the AC electroosmotic flow to induce an electrohydrodynamic potential, which enables us to trap particles in the sub-10 nanometer size regime and to trap them at a trapping location, which is several microns away from the laser spot, where they can experience the ambient temperature and the ambient light intensity, so there's no damage to the objects. And subsequently, I also introduced another capability of this OTET platform, namely the ability to achieve the two-dimensional manipulation of sub-10 nanometer protein particles. So in this case, we've used a BSC as a model protein. And I also show you the ability to achieve the size-based sorting of sub-100 nanometer size objects, which falls within the size range of exosomes and exomex, which are part of the subpopulations of extracellular vesicles. So I'll show you how we can sort particles within this size range by using this OTET platform. Okay, so basically this is the OTET platform. It basically comprises of laser illumination of plasmonic and nanohole array, and then we can cause some particle here, let's say a protein molecule here, to experience a force several microns away from where the laser is, and it can be trapped at that position. So here, where the object is trapped is a region of ambient temperature and also ambient light intensity. So the protein or any molecule is not going to be damaged due to the hot this heat induced by this nano antenna array here, this nanohole array. So let's see how this works. So the mechanism that OTET works basically employs two opposite microfluidic flows. So what happens is when we illuminate this nanohole array with light, so they basically absorb the light and then they dissipate heat. So this is the whole idea of thermoplasmonics. So they absorb the light and they generate some local heating effect. So that heating effect then gets transferred to the fluid, and that establishes a thermal gradient in the fluid. So when you have a gradient in the fluid, if we apply an AC bias, we're going to induce an electrohydrodynamic flow called the Electro-Thermo-Plasmonic flow. And I'll talk about that in a little bit. So the Electro-Thermo-Plasmonic flow is actually radially inward in this case, trying to transport particles towards this hot region. And also because of the fact that you have this whole array, the whole array is going to distort the perpendicularly applied AC electric field, and that is going to create a tangential component. So that tangential component of the field can then act on the diffuse charges in the electrical double layer induced at the interface between the fluid and the nanohole array surface. And that action of the electric field on that diffuse charges induces an electroosmotic flow, which in this case is radially outward. So at some point, both flows are going to balance each other, and that defines where the traveling position occurs. And that's usually several microns away from where the laser hotspot is, and also from the edge of this nanohole array. So let's first look at the concept of this Electro-Thermo-Plasmonic flow. Then we'll discuss about the AC electroosmotic flow, and then see how we can combine both to induce this electrohydrodynamic potential. Okay, so the ETP flow concept, as I mentioned before, basically happens if we simply illuminate a nanohole array, with light. So we induce this gradient in the temperature of the fluid, which in turn results in a gradient in the permittivity and the electrical conductivity of the fluid. So we have a gradient in the electrical conductivity of the fluid. In order for Gauss' law and the equation of charge conservation to be simultaneously satisfied, we're going to have the creation of a net charge in the volume. So the AC electric field can act on that induced charge and cause them to move, and in the process, you induce a hydrodynamic flow, which is this Electro-Thermo-Plasmonic flow. So key things we need is laser-induced heating as well as an AC electric field is applied. So you have the laser-induced heating and the AC electric field. And in this case, this Electro-Thermo-Plasmonic flow is radially inward. So it's acting to transport the particle towards the region where the laser hotspot is. So that's one of the key flows that we leverage. Okay, so now what about the AC electroosmotic flow? So let's consider if you have a gold nanohole array, and then you have another, let's say you initially have a gold film, and then you have an electrode. If you apply an AC bias, you're supposed to have a uniform field, just like a parallel plate capacitor, except on the edges is where you can have this fringe field. But far away from the edges, the electric field is supposed to be uniform. However, if I structure the gold surface, the gold film, with some nanoholes, then what is going to happen is this nanohole array is going to perturb the electric field. So I'm going to end up with a field gradient. So that means I will have a tangential component, the normal component as well as a tangential component. And it's that tangential component that we're interested in, because the tangential component can actually act on the diffuse charges in the electrical double layer, which are able to move. And then it's going to cause those diffuse charges to move, and in the process, they're going to drag the fluid, and that's a mechanism called electroosmotic flow, AC electroosmotic flow. So that happens here because we have those in nanohole array. So in order to model these flows, what we'll do is we'll start from electromagnetic wave equation derived from Maxwell's equations. Then we solve that. So we find the electric field in the vicinity of the nanohole array and the fluid. So knowing that electric field, we use that to compute the heat source density, which is given by half of the array part of this conduction current density J and E. And then once we know the heat source density, that serves as a source term in the heat diffusion equation, which we solve numerically to find the temperature field in the system. So knowing the temperature field in the fluid, we can then proceed to solve the Navier-Stokes equation in order to find out the velocity of the fluid for the different flows in consideration. So to model the electrothermal body force or the electrothermo-plasmonic flow, we use this expression here, which is derived from a perturbative expansion of the previous formula that I showed. You can also have convection, which is due to change temperature gradient that causes a change in the density of the fluid. However, in this case, convection is actually weak, so it's usually negligible. But the main flow that is strong here is the AC electrothermo-plasmonic flow. So that's how we include that. And these expressions, alpha, differential change in permittivity with temperature is given by this expression. Excuse me. So we use these two terms as a forcing term in the Navier-Stokes equation. Okay, now, in order to include a contribution from the AC electroosmotic flow, we basically add this by prescribing a slip boundary condition in the region of the nanohole array. So the slip boundary condition is given by the Smoluchowski slip velocity U, which is given by this expression, mu times E. E is the ET, the tangential component. So this mu electroosmotic is given by this expression. So this eta here is the zeta potential of the electrical double layer at the interface between the nanohole array and the fluid. And then this mu is the dynamic viscosity of the fluid. So this, this E sub T, which is a tangential component, is really simply the total electric field minus the normal component. So once we know that, we can then plug it into this expression for the Smoluchowski slip velocity, and we use that as a boundary condition in the region containing nanohole array. And that's how we include the contribution from the AC electroosmotic flow into the equation. And the zeta potential itself is frequency dependent. So by tuning the frequency, we can change the zeta potential, and that can tune the strength of this AC electroosmotic flow. And later on, I will show how we can use that to induce some interesting phenomena, in this the traveling performance of OTG. Okay, so using this, when we model this problem, this is the flow field distribution that we get. So I'm showing you the one along the in-plane direction. So that is XY plane. So you notice that you can see the vector for electrothermo-plasmonic flow is radially inward, while AC electroosmotic flow is radially outward. So at some point, both of them are going to meet up. And once they meet up, they're going to cancel each other, and the fluid velocity is going to go to 0 at that region. And that is going to define the stagnation zone, that's going to define where the particle is going to be trapped in OTET. And by tuning the frequency of the AC field, we can actually shift this stagnation zone. And that is what we show here. So if we look at for different frequencies, we can control where the velocity goes to 0. That is the stagnation zone. So you notice that for smaller frequencies, it's actually closer to the edge of the, for larger frequencies, it's closer to the edge of the pattern. But as you increase the frequency, then you can shift the particle further and further away. So that way we can tune the position that the particle is trapped by simply tuning the interaction, the interplay between this AC electroosmotic flow and the electrothermo-plasmonic flow. Another interesting thing is, if you were to move the laser spot from one point to another, let's say along this direction, so the flow field, because the ETP flow is dependent on the thermal hotspot, so it's gonna move, and that kind of biases the flow field and makes the stagnation zone to be moving. So the particle is gonna move along that direction. So we can have dynamic manipulation capability by simply translating the laser beam and hence the thermal hotspot from one position to another. Again, the particle is always trapped several microns away from where the hotspot is, which is one capability of this, key advantage of this platform. Okay, so we also characterize the trapping stability for OTET. So what we find is that the trapping stability is actually quite pretty good, and it's actually more enhanced along this direction, which is the X direction, which is direction that is parallel to this edge of the nanohole array. And along this direction, the trapping stability is weaker. And that is because there's a direction where both flows are trying to cancel each other. So that's why you have a weaker trapping stability. But in this direction, you have a higher trapping stability, which is what we show here. And this is a single object that has been localized here, a single protein, where your laser spot is here and the particle is being trapped in this position. So here is a video showing the trapping. So initially that's your laser spot, and you see the particle being transported, and at a frequency of 3 kilohertz is being trapped at that position. Oops. Let's play that again. So the particle is being transported, and this is where the stagnation zone occurs, and it gets localized there. So it never moves towards the laser spot to feed the heat. So it just remains trapped far away from where the laser spot is. And this process also happens within a few seconds, like less than 3 seconds in this case. So here we have the ability to trap things very, very fast, and we also solve the problem of heating effect, at the same time. So what about dynamic manipulation? So that is also a feature that is possible here, as we show from the experiment. So here you have the laser beam, and that is the object being trapped. So as we move the laser beam up and down, the object actually follows the direction of the laser beam. So you can actually dynamically manipulate the particle that has been trapped from one point to another. So it's not limited to just a given point, but you can actually move them from one location to another. And also, very crucially, is the particles are also being trapped far away from where the laser spot is. So there is no potential for any photo-induced damage, like photothermal heating or from excessive light intensity from biological molecules. So the biological molecules get to experience ambient temperature and also ambient light intensity while being trapped. So basically, we can harness plasmonic heating to trap sub-10 nanometer biological molecules, use plasmonic heating to advantage, but then we also ensure that the heating does not constitute a problem by ensuring that the heat never interacts with the particle that's been trapped. So that is a way to summarize the capability of this new kind of optical nanotweezer. So another important advantage or key feature is really how can we sort particles based on size. So here we sorted 2 particles that are the size range of 20 nanometer and 100 nanometer. Okay, so these are polystyrene based. So what happens is if we tune the AC frequency to about 2.5 kilohertz, so we can trap both the 20 nanometer and the 100 nanometer size bits. Now, we can keep them to remain trapped as we continue to increase the frequency. However, when the frequency of the AC feed gets to about 4 kilohertz, then the 100 nanometer size object gets released, while the 20 nanometer size object still remain trapped. And that way you can trap a smaller object and release a bigger size object. So most of the techniques for doing sorting are usually able to sort out, let's say, bigger size objects, versus smaller size objects, typically. But here I can easily sort out the smaller size objects and spare the bigger size objects. And the reason why we can release the 100 nanometer size objects while keeping the 20 nanometer size objects is because the force that enables the trapping of the particle in the out of plane direction is due to the interaction between the surface charge on the particle and the surface charge on the surface of the nanohole array, in the electrodouble layer. So now we know that when you have the particle inside the fluid, there is going to establish an electrodouble layer, which is going to try to screen the surface charge. So the electrodouble layer around it is a loosely layer of band charges. So when you apply the AC electric field, the electrodouble layer charges are going to move in response to the field. So the electrodouble layer will be polarized. So for bigger sized particles, they're going to take a longer time, for them to move and be polarized compared to smaller sized particles. So that means the smaller sized particle and the bigger sized particle have different charge realization frequencies. So if we are able to increase the frequency, higher, if we do that, then we can ensure that the bigger size particles, they don't have sufficient time. The electrodouble layer charge there do not have sufficient time to respond to the AC electric field, and as a result, they're going to feel less force in the out of plane direction and escape. So that's how we're able to achieve the sorting in this case. So let me show you the video again. So that is 20 nanometer, 100 nanometer sphere. And then as we increase the frequency of the AC field, we can then release the bigger size particle while keeping the 20 nanometer size particles still remain trapped in place. Okay, so just to give you like a summary and a brief, this is quite an incomplete milestone on the accomplishments in the field of optical nanotweezers over the years. So it's as follows. First in 1986, after Ashkin introduced the single beam optical tweezer, which enables the trapping of microscale particles. And subsequently, this was used to achieve the trapping and cooling of atoms under very, very low temperatures, for which Stephen Chu, Kohei Tanoji, and William Phillips were awarded the Nobel Prize in 1997 in physics. Then in 2018, recently, just 2 years ago, Ashkin was recognized for the development of optical tweezers and for their use for biology applications, because optical tweezers have enabled scientists to be able to do force measurements, to understand, for example, DNA mechanics and the mechanics of other molecules with very, very high resolution. So this was why Ashkin was recognized with the Physics Nobel Prize for being the first person to introduce these optical tweezers. Back in 1998, Lucas Novotny actually suggested the idea of having a tweezer on the tip of a fiber. And this, basically, the idea was to use a vanishing mode from this, from the tip of the fiber to enable the trapping of smaller particles, which can give you better confinement due to the high K states of the vanishing modes compared to regular free space optical tweezers. And that was actually what really stirred interest in the field of plasmonic tweezers as ways to really achieve more localization of your optical modes to enable trapping of very small objects. So one of the key contributions, key developments in the field was the concept of self-induced back action, which was explained by Roman Guidan's group. And then you also have several other works by Ken Crozier, and some earlier was by Green Koreko from University of Manchester. And then using this self-induced back action to trap a single protein molecule was achieved by the Ruve and Gordon group from University of Victoria back in 2012. And as we came to learn over the years, plasmonic tweezers were always limited by the inability to rapidly transport particles for trapping. So instead of having to rely on diffusion to load the trap, so we introduced this concept of electro-thermo-plasmonic tweezers. And then recently, we've just launched this concept of Opto-Thermo-Electrohydrodynamic tweezers, which should be appearing online soon in Nature Nanotechnology, where we show the ability to be able to trap particles far away from the laser beam, while still preserving the capability to trap particles in the sub-10 nanometer size regime, and also the ability to dynamically manipulate the particles, as well as the interesting added feature of the ability to sort particles. in the field. So we believe that this should enable some interesting developments and new kind of applications, which I will highlight in a little bit. So just to summarize, so I've talked to you, introduced to you today about a new kind of optical nanotweezer, which we've called Opto-Thermo-Electrohydrodynamic tweezers, that enables the nanomanipulation of sub-10 nanometer biological molecules, whereby they can be trapped at a distance of several microns away from your hot plasmonic nano antennas, so that these particles never get to experience heating effect from your laser beam. And we also show the capability to stably trap sub-10 nanometer size objects, and also with important feature that one eliminates any risk of photo-induced damage to biological molecules. And this has been an issue that has been limiting the translation of plasmonic tweezers to myriads of applications in biology. So in life science, there are a whole lot of tools, a whole lot of ways that, new kind of nano tweezers that have better performance, that overcomes the limitations of conventional optical tweezers, can enable some very, very interesting applications. And this has been limited so far because of these issues of photo-induced damage to biological molecules. So we believe that with this Opto-Thermo-Electrohydrodynamic tweezers, OTET, that this now opens up the door for many, many exciting applications. So some of them I've cited here, including high performance nanobiosensors. For example, this platform can be used to capture very small molecules like protein, that can be antibodies or antigens released by some, let's say, viral infection, for example, and then they can be trapped. And also one can do in situ spectroscopy, let's say via fluorescence, to be able to detect these antigens of interest. And this can be done very, very rapidly. So, for example, the protein molecules we're trapping, in those experiments, we actually diluted to femtomolar concentration, which is an extremely small concentration. So that means one can do sensing at such a small concentration rate. And that was the smallest that we've tested. Who knows the limits? Perhaps we can even push that further. Also, another interesting possibility is in the area of single molecule Foster resonance energy transfer spectroscopy. So typically doing this kind of Foster resonance energy transfer spectroscopy, people have suggested using confocal microscopy to do that. But because of the fact that small molecules diffuse very, very fast, if you look at Extens-Brownian diffusion equation, you discover that the diffusion coefficient is inversely proportional to the size of the particle. So very, very small particles diffuse very, very fast, and they can readily escape from the observation volume. And that the result is that people typically just see bursts of signals, and it becomes very hard to interpret the data. So it's of interest to be able to localize your single molecule within the observation volume for long-term observation, so you can understand the interaction between donor and acceptor molecules for threat studies. And that's a capability that can be enabled by these Opto-Thermo-Electrohydrodynamic tweezers. Also, in the field of extracellular vesicle research, so we see some huge opportunities here because currently it's not known how the size of EVs help to detect their functions. So having a tool that can allow us to be able to sort EVs of different populations for study will be an important step towards answering some of these important fundamental life science questions. And with this, I'd like to thank members of my team who have been working with me over the years in the past few years to solve some of these problems in the field, and also thank NSF for support. I'm going to leave the slide here, and I'm sure there are questions. I'll be happy to take your questions. Thank you.
Thank you. Thank you, Justus. This was it's really great. Quite neat idea and application. So it's very nice work. So we had a question before. So from Brian. So maybe okay. So Brian, you can ask him yourself if you want. You can talk now, I think, if he's there. Brian. Right. maybe, I don't know, we type the question. Well, in the meantime, I have, so while we collect other questions, I also have a few myself, actually. So can you go, so when you described at some point all the forces that allow you to create this stagnation zone around the array, can you just go back there a second and just recap them? Because I think I missed like one step. So what's the, so I understand, yes, exactly. So yeah. So basically, well, first of all, so the array that you need, like how, I mean, what's the size of the beam compared to the size of the array? I mean, is there any specific optimization in that, or you just want to create a thermal gradient without very?
Yeah, so we just want to get thermal gradient. So if your beam is tightly focused, you can do that, easily. So the size of the array can be, say, 20 micron by 20 micron, for example. And then the beam spot size can be, say, 1, 2, 3 micron.
Okay.
So that's going to give you enough thermal gradient.
Okay. And okay, so you have your array in the let's say in the center. Then, so the particles that you because from the SEM images, like there was like a contrast in the image. So what do you have outside the array? It's like, so where do you put initially the particles that you want to track?
You mean,
yeah,
okay.
like here.
Here is just this is just a gold film. This is the region with the whole array.
Okay, so everything is gold, then there is the array in the center, and you put the particles in the film, far from the array.
Yeah, the particle is far from the array, yes. And
right.
also far from the laser spot.
Okay. So now basically the force I was missing is, so you have the thermal gradient that goes one direction, then what is that pushes, that let's say that pulls away the particles from the array?
That's the nice... is the AC electroosmotic flow. And that's the one that tries to push them away. So it's radially outward. And that arises because, so if you have the whole array, so this region with the whole array, if you apply your electric field, there's going to be a gradient in the field. So that means you have an axial component, and you're also going to have a tangential component. Mm-hmm. So that tangential component can then act on the diffuse charges in the electrical layer. So that diffuse charges are always formed anytime you have a solid surface and a fluid, at the interface between the solid and the fluid. Insofar as there's some ions in the fluid, then that electrical layer will be formed. So it's basically a loosely bound layer of charge that tries to screen the surface charge. So you have, assuming this is a negatively charged surface initially, you're going to have a positive charge ions here, and then they attract negative. This negative attract positive, and so on. So within this region, the charges are kind of loosely bound. So this tangential electric field can act on the charges and make them to move. And that creates the electroosmotic flow, which in this case is radially outward. Yeah.
Okay, I see. Okay. And so basically, and also I guess that changing the strength of the AC field, you can also change the position of this stagnation zone to some extent, at least. I mean, if you push them.
Yeah, possibly, yeah. But the more elegant way we do that is by changing the frequency of the AC field. The reason being because since the electroosmotic flow is dependent on zeta potential, and then the zeta potential is itself dependent on the AC field frequency. So if we are varying the AC field frequency, we can be varying this electroosmotic flow, and by so doing, be shifting the stagnation zone. So basically, at lower frequencies, the electroosmotic flow is stronger, and that's why the stagnation zone shifts further away.
Okay, I see. Yeah, makes sense. Thank you. Okay.
You're welcome.
Okay, so maybe Brian is back. Give me a sec. Okay, Brian, you can ask your questions. Do you have a couple? Or maybe, well, maybe you cannot talk. So, no, okay. Okay.
Sorry about that.
No
yeah,
problem.
the question, it doesn't really have a ton of bearing on the current work. It was basically just asking what limits we can heat up organic materials until we start to lose what we're looking for. But I'm guessing there's some sort of dampening effect that just keeps the nanoparticles from just oscillating around the stagnation zone instead of staying within it? Or is there something else at play that I'm just not taking into account?
Okay. Yeah, that's a good question. Yeah. So the dampening effect or the force that makes it to stay within that stagnation zone is also comes from the axial component, the axial force, and that is really the electrostatic interaction between the particle and then the diffuse charge in the around the nanohole array. So it's basically an electrophoretic force that acts on the particles in the out of plane direction. So once you're in stagnation zone, that makes them to keep on to stay, on the surface of the electron.
Okay. Thank you.
Okay. And so, well, like a connected question regarding to the temperature. So here, what is, you said that, well, through this technique, basically you avoid the particles to go where the temperature is the highest, but still you need this temperature gradient. So what are the, let's say, the minimum temperatures that you need in the beam spot, even if you don't touch it with the particle, but still, what type of temperature you have to deal with?
Okay, yeah, so the temperatures are actually easy to accomplish. So just a few degrees rise above room temperature is already sufficient to induce this electro-thermo-plasmonic flow, because really the strength of the electro-thermo-plasmonic flow comes from it scales as the electric field squared. So I can always increase it as much as I want by simply increasing the electric field. And also very crucially, the electro-thermo-plasmonic flow is dependent not just on the temperature, but actually the temperature gradient. So what really matters is the confinement of the temperature field. So you can have a strong gradient, not so much on the actual temperature rise. So just a few degree rise, but so far it's highly confined, already suffices for this.
Okay. Oh, interesting. Okay. And so there, let me see here. So any other questions from the other attendees? Well, if something comes up, they can type it. And just I had a curiosity about so this all these forces. So what's the range of the strengths of the forces that you are dealing with here? Like, are they like piconewton or nanonewton, something?
Okay, that's a good question. So I would estimate they'll probably be in the piconewton or fraction of piconewton range by looking at probably a fraction of the piconewton, I would assume, by looking at the strength of this trapping stability. We haven't really calculated the actual number, yeah, but from this data we can get that.
Okay, yeah, because I knew that piconewton was kind of the regime for acting on biomolecules, so I guess that has to be kind of consistent with that. So that makes, if it's piconewton, then I think that makes a lot of sense. And have you tried? So if you wanted to trap bigger parts, so what's the upper limit in terms of size? So you said that if you lower the frequency, you can keep track larger particles. Is there any limit in that? So have you tried like even bigger particles, say 1 micron, or then you have troubles?
Yeah. So I would assume that the limit, maybe one may be able to trap probably up to about a micron without having to reduce the frequency, that significantly, and possibly also by maybe changing the content of the, let's say by the conductivity of a fluid solution, might allow one to be able to tune that to an extent. But we haven't really investigated what will be the upper limit, because we are more kind of interested and focused on things that are on the sub 100 nanometer size regime and sub 10 nanometer, given those are usually traditionally more difficult to do. But I would imagine, let's say, probably up to about a micron, before one has to reduce the frequency to too low a value.
Okay. So it's actually a very big range. This is from like 10 nanometers, 10 microns. It's kind of you have a lot of capability there. Okay.
Right.
That's and have you? Well, I guess this is of course is the first work on this. But then, can you envision to have like a second laser just to test basically what you said in the outlook and next steps? So envision to have like two lasers, one that produces the thermal gradient and the other one that kind of does sensing of the threat particles. Do you think it's feasible? I mean, from the technical point of view, is it something that you see practical or no?
Yeah, absolutely, yeah. So one can certainly have one laser to be doing the trapping, and then another one to be doing probing. Let's say with a low intensity, so that you don't damage the object that you're trying to probe.
Right.
Yes, that is certainly possible. Yeah. Another aspect we're also investigating is also ways to kind of even increase this trapping stability even further, so that one can have a much tighter confinement. So that's one of the areas that we're currently investigating.
Okay. Wow. Yeah. So is that what's your next step in here? Are you will you keep working on this type of application? Have you? What's your mind now? What's your plan?
So we are now working to put this to use for several of the applications, like some that I discussed.
Mm-hmm.
So one of them is like applying them towards extracellular vesicles research. So we'll be doing some investigation in this area, being able to trap and manipulate the exosomes and be able to analyze them, which we believe will enable us to answer some important fundamental biological questions, in the field. So one interesting possibilities is also for single molecule threat studies. That's also another area that we're quite interested in exploring. And I'm also eager to see how other researchers worldwide would use their imagination to adapt the tool to towards some other interesting possibilities as well that we'll consider.
Yeah, it seems there are really a lot of possibilities also because basically what you need to trap those particles, so they just need to basically have they need to be polarizable. That's it. And then you can tune the parameters to make it trap where you want. But is there any other constraint on the particle itself that you want to trap besides that they're going to have some surface charges at some point? Or
no constraint that we have experience or thought about. This basically works for dielectric particles, which most biological molecules are dielectric.
Right.
And being able to acquire surface charge, is pretty easy. So molecules can really get surface charge from their solution, and once that is formed spontaneously, they can also quickly immediately establish an electrical double layer. So we don't have to add, for example, let's say surfactants, any of those kind of solutions. No. So
right.
Just put your solution in water, and it works.
Yeah. Okay. Yeah. That's. Thank you very much. That was really interesting.
It looks like there are some questions on the chat. Did you check?
Other questions?
Did you check if there are any questions on the chat, Manny?
I see two but those were from Brian before. Do you see more than other questions? Because maybe
no, I saw two, but I couldn't view them.
No, okay, yeah, those were from Brian before the regarding the temperature and the damping. So yeah, those were the two that we got before.
Okay, sounds good.
Okay. So I don't know if there is no other questions, then anybody? Okay. No, not at this time. But so Justus was very kind before. So he told me that if you had any question about the talk, about these articles and application that he presented, just feel free to email him, I guess. and he's going to be more than happy to reply to any question you have. So please do that if you have something, because I mean it's great that you can have direct replies from one of the top experts in this. So I really suggest you to exploit this this opportunity. For that, okay, with that I think that we can. If there isn't anything else, we can close the recording, and then I'll talk to you, Justus, in 2 minutes on another channel. And again, thank you very much to everyone for following the talk, and thank you, Justus, for giving this great presentation.
Yeah, thank you all. Thank you so much.